Now, mass energy relation. So initially scientists thought like this: in any type of reaction, total mass and total energy conserves independently. Okay. But later on, when detailed studies related to the nuclear reactions were carried out, then they observed this thing: when the reaction takes place at that time, the total mass on left hand side and total mass on right hand side, that is not same one. So Einstein represented this thing at that time. Mass is a form of energy. So independently mass and energy are not conserved. Mass and energy conserves jointly. And the relation between mass and energy he gave, that is E equal to mc square, where c, that is the velocity of light in vacuum. Its value, that is 3 into 10 raised to 8 meter per second. It implies that when m kilogram mass convert into energy as per this equation mc square, then we will get energy equal to E. Now see, we already discussed this thing. In atomic and nuclear physics, we use the unit of mass, that is atomic mass unit. That is atomic mass unit. Okay. And it is represented by U. So let's calculate one U energy when one U mass when convert into energy. Then how much energy will be obtained? So mass will be converted into energy as per equation E equal to mc square. So E equal to mass, that is 1U into c square, that is 3 into 10 raised to 8 whole square. But 1U mass, that is 1.66 into 10 raised to minus 27 kilogram. So we can write here 1.66 into 10 raised to minus 27 into 3 into 10 raised to 8 whole square. Now when we solve this one, we will get 1.4924 into 10 raised to minus 10 joule. Now divide this one by 1.6 into 10 raised to minus 19, we will get energy in electron volt. So 0.9315 into 10 raised to 9 electron volt. So we can rewrite this one as 931.5 into 10 raised to 6 electron volt. But 10 raised to 6, that is mega or million, we can say. So when 1U and mass is converted into energy, then the energy obtained, that is 931.5 MeV. So this one is the mass energy relationship. Clear to all of you? Example 13.2. Calculate the energy equivalent of 1 gram of substance. So mass given to you, that is 1 gram, that is 10 raised to minus 3 kilogram. As per equation E equal to mc square, one can calculate the energy. Mass, that is 10 raised to minus 3 kilogram, C 3 into 10 raised to 8 whole square. So resultantly, we will get 9 into 10 raised to 13 joule. If you want to represent this one in electron volt, then divide this by 1.6 into 10 raised to minus 19. You will get your answer in electron volt. Clear? The next topic, that is nuclear binding energy. Now, see here, actually when we think about the protons and neutrons in independent state, free state, and when they combine to form any element, So at that time there is the mass defect. Now what is the exact meaning of this mass defect? Let's understand this thing. Now we know mass of proton, that is 1.00727 U. Mass of neutron, that is 1.00866 U. And now suppose we take mass of oxygen atom, then oxygen, that is 8O16, its mass, that is 15.99493 U. Okay. હવે આપણે લોજિકલી વિચારીએ તો જો શું થાય કે એકચ્યુઅલી ઓક્સિજનની અંદર 8 પ્રોટોન છે. 16, that is atomic mass. 16 minus 8, that is 8 neutron number. એટલે ઓક્સિજન એટમની અંદર ન્યુક્લિયસમાં 8 પ્રોટોન છે ને 8 ન્યુટ્રોન છે. Now we have mass of 1 proton. It implies that mass of 8 protons, that will be 8 into 1.00727, and it will come to 8.05816 U. Then if we take mass of 8 neutrons, then that is 8 into 1.00866 upon into 8. So we will get resultant 8.06928 U. Now logically we can say this thing, when 8 proton and 8 neutron combine to form oxygen atom, then the total mass, that should be 8 MP plus 8 Mn. So mass of 8 protons, that we calculated 8.05816, and mass of 8 neutrons we calculated, that is 8.06928. If we take the summation of these two, then our answer will come to 16.12744 U. So logically આપણે જોવા જઈએ તો 8 પ્રોટોન અને 8 ન્યુટ્રોન ભેગા થાય ને તો ટોટલ માસ આટલું થવું જોઈએ. પણ એકચ્યુઅલી જ્યારે ઓક્સિજન એટમનું ફોર્મેશન થાય છે અને એ એટમનું જો આપણે માસ લઈએ તો એ 15.99493 U થાય છે. હવે જો આપણે આ બેનો ડિફરન્સ લઈએ 16.12744 U minus 15.99493 U, then it will come to 0.13251 U. So આ જે mass missing છે, that is mass defect. Actually that particular mass is converted into energy as per Einstein's equation, E equal to mc square. So here this delta M mass, which is called mass defect, converts into energy. So that energy delta M into C square, that is called binding energy of the nucleus. Means with this much energy, the nucleus is bounded. So we can write the equation for mass defect delta M, that is total mass of number of protons in free state plus total mass of number of neutrons in free state minus mass of that element. That is mass defect and binding energy of nucleus, that we can give by delta M into C square. Suppose this binding energy is divided by atomic mass number, then we will get binding energy per nucleon. એટલે આનો મીનિંગ એવો થાય કે જો બાઇન્ડિંગ એનર્જી ઓફ ન્યુક્લિયસ આપણે લઈએ, ધારો કે અહીંયા આગળ આપણને માસ ડિફેક્ટ For oxygen, that is 0.13251 U. આટલી મળી. હવે આપણે આગળ ઉપર કેલ્ક્યુલેટ કર્યું કે 1 U that is 931.5 ઇલેક્ટ્રોન વોલ્ટ. તો આટલા U એટલે કેટલા ઇલેક્ટ્રોન વોલ્ટ? તો હવે this one multiply by 931.5 કરીએ તો એટલા ઇલેક્ટ્રોન વોલ્ટ એ ઓક્સિજન ન્યુક્લિયસની બાઇન્ડિંગ એનર્જી થઈ ગઈ. એનો મતલબ એ થયો કે this particular nucleus is bounded by this much energy. So if that much energy is given to that nucleus, then the nucleus will be broken up. The nucleons in the nucleus will be free from it. And now if binding energy is divided by the number of nucleons, means atomic mass number, then we will get binding energy per nucleon. એટલે કે જો આપણે બાઇન્ડિંગ એનર્જી પર ન્યુક્લિયોન જેટલી એનર્જી સપ્લાય કરીએ તો એક ન્યુક્લિયોનને આપણે ફ્રી કરી શકીએ. This is the concept of mass defect and nuclear binding energy. Clear to all of you? See, here in this graph, we can observe this thing. For atomic mass number 30 to 170, the variation in binding energy per nucleon that is very small. So we can consider the binding energy per nucleon in this particular range is almost constant. See here, curve have maximum binding energy, that is for Fe 8.75 MeV, and for A equal to 238 it is 7.6, somewhere here it is 7.6 MeV. So variation is very small. But here see, now binding energy per nucleon, that is the measure of the stability of nucleus. જેમ binding energy per nucleon વધારે હોય એમ આપણે ન્યુક્લિયોનને ન્યુક્લિયસમાંથી ફ્રી કરવા માટે વધારે એનર્જી આપવી પડે. તો જે ન્યુક્લિયસ માટે બાઇન્ડિંગ એનર્જી પર ન્યુક્લિયોન વધારે હોય, that particular nucleus is considered as most stable nuclei. And see, graph represent this thing. For Fe, binding energy per nucleon, that is maximum one. For Fe, A that is equal to 56. And for that binding energy per nucleon, that is 8.75 MeV. So iron, that is the most stable nuclei. Okay. And see here, now on lighter side, એટલે કે atomic mass number less than 30 જઈએ આપણે. અને પછી for heavier nuclei, એટલે 170 થી ઉપર જઈએ આ બાજુ, right? તો binding energy per nucleon decrease થાય છે, right? તો સ્ટડી આપણને આવું બતાવે છે. Graph clear? Now from this graph we can conclude something related to the nucleus here. This binding energy per nucleon, which one is representing how strongly the nucleus is bounded, which suggests this thing, the attractive forces in the nucleus are sufficient strong, clear? As well as this binding energy also represent this thing, these particular forces are short range forces. It implies that the distances between nucleons, if it is very less, then only this particular nuclear forces will be effective one. And here we can observe this thing when heavy nuclei, say here on this side, if heavy nuclei is broken up and converted into lighter nuclei. આપણને સિમ્પલ ટેક્સ્ટમાં એક્ઝામ્પલ આપ્યું છે કે A equal to 240 વાળું ન્યુક્લિયાઈ સપોઝ 120 ના બે ન્યુક્લિયાઈમાં ડિવાઈડ થઈ જાય, રાઈટ? તો 240 માટે એનર્જી that is here less than 8 આવશે. But when it is converted into two lighter nuclei of A equal to 120. So here we can observe this thing for that the binding energy per nucleon that is greater than 8 MeV. Clear? So heavier nuclei, when it is divided in smaller nuclei, at that time the energy releases. When binding energy per nucleon increases, it implies that energy releases. And this particular process that is called fission process. In the same manner, here see, we can observe this thing for lighter nuclei, the binding energy per nucleon that is less. But when these lighter nuclei combine to form the heavier nuclei, so when heavier nuclei is formed, then again we can observe here for heavier nuclei, the binding energy per nucleon increases. So when binding energy increases, the energy will be released. Okay. So this particular process in which lighter nuclei combine to form the heavier nuclei, that process is known as the fusion process. So either the fission or fusion takes place for the nuclei, the energy that will be always released. Clear to all of you? Example 13.3. Find the energy equivalent of one atomic mass unit, first in Joule and then in MeV. Using this, express the mass defect of oxygen 816 in MeV per C square. Now see, we already discussed Einstein's equation, means mass energy relationship E equal to mc square, where C, that is the velocity of light in vacuum. Now, if 1 U mass is converted into energy, then how much energy will be obtained? So energy equivalent to 1 U, that is E equal to 1 U into 3 into 10 raised to 8 whole square. 1 U, that is 1.66 into 10 raised to minus 27 into 3 into 10 raised to 8 whole square. So solve this one, we will get answer in Joule. Then divide it by 1.6 into 10 raised to minus 19. We'll get 0.9315 into 10 raised to 9 electron volt. You can rewrite it as 931.5 into 10 raised to 6 electron volt. So we will get 931.5 MeV energy when 1 U mass is converted into energy. Now we have to express the mass defect of oxygen in MeV upon C square. So here see, E, that is mc square, so M, that is energy upon C square. Now mass defect for oxygen, that is 0.13251 we calculated earlier, and 1 U, that is 931.5 MeV. So if 0.13251 is multiplied by 931.5, then we will get here some answer But now the unit that we can write here, MEV, and from left hand side delta M into C square is taken on right hand side. So we can write here MEV upon C square. And in question, it is asked represent or express the mass defect in MEV upon C square. Clear to all of you? Next topic, that is nuclear force. Now see, one can easily understand this thing. Here nuclear force, that is too much strong force compared to Coulomb force, or we can say gravitational force. Gravitational force is weakest one. Coulomb force is stronger than gravitational one. And this one is stronger than the Coulombian force. How we can say? See here, nucleus is made by protons and neutrons. Neutrons are electrically neutral. Protons are positively charged particles. So between positive charges, the Coulombian repulsive force is there. But here we observe this thing, nucleus is strongly bounded. Tremendous large amount of energy is required to break up the nucleus. It implies that definitely some force is there in the nucleus, which one is stronger than the Coulombian force. And under the effect of that particular force, all these nucleons are strongly bounded. Clear? Okay. And this binding energy per nucleon and all these calculations suggest this thing, this particular force, that is short range force. It implies that this particular force that will be exerted by one nucleon to another nucleon within very short range, or we can say when two nucleons are neighbor, in that particular case this force will be effective one. And this particular range, that is of the order of Fermi, 10 raised to minus 15 meter. And here, suppose we draw the graph of potential energy versus distance between nucleons, then the graph that will be as shown in the figure. And here we can observe this thing. At a distance R0, which is nearly equal to 0.8 Fermi, the potential energy that becomes a minimum one. Okay. So here we can say in this particular situation, stable equilibrium will be there. And here we can observe this thing, as the distance increases than this one, then here we can observe this thing, potential energy increases and reaches close to 0. Means here the forces rapidly decreases. Clear? So this particular force, that is short range force, and we know this thing, force F, that is minus du by dx, 11માં ભણેલા છીએ આપણે. The negative of the rate of change of potential energy with respect to distance that give you force. તો જો 0.8 Fermi થી distance increase થાય ને, એટલે forces attractive બને. કારણ કે force ની value negative આવે આ side ઉપર. And negative force represent attraction. અને જો 0.8 Fermi થી force distance decrease થાય તો force એ positive થઈ જાય. તો એ repulsion બતાવે છે. Clear? And here we can observe this thing. This nuclear force equally prevails between proton, 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 neutron, and neutron, neutron. Irrespective of the type of particle, this prevails between the constituent particles, means protons and neutrons. And therefore, when we deal with nuclear forces at that time, collectively we say these constituents as nucleons. Clear to all of you?
Yes, sir.
Now, next topic, that is radioactivity. Actually, this phenomenon of radioactivity was discovered accidentally by Becquerel. He was studying about the fluorescence and phosphorescence like this. And in these experiments, he observed this thing. Some invisible radiations comes out from the heavy element, and it affects the photographic film. So from that, he discovered this phenomenon. Radioactivity means what? Naturally, some heavy elements like uranium, polonium, radium emits some radiations continuously and spontaneously. This phenomenon of emission of radiations continuously and spontaneously from heavy nuclei, that is called radioactivity. So in other words, we can say naturally heavy nuclei or heavy elements undergoes decay. And when detailed studies related to this phenomenon of radioactivity was carried out, scientists came to know about this thing. 3 types of emissions takes place here. Alpha emission, beta emission, and gamma emission. Or it is known as alpha decay, beta decay, and gamma decay. Alpha decay. Actually, alpha decay or alpha emission, that is nothing but particle emission. And alpha particle, that is the helium nuclei. That is helium nuclei. Then beta decay or beta emission, that is also particle emission. Beta particle itself is electron or positron, right? 2 types of beta particles are there, represented as beta plus, which is positron, beta minus, that is electron. Clear? And gamma decay or gamma emission, that is nothing but the emission of energy in the form of electromagnetic waves, or we can say that is nothing but the emission of energy in the form of photons. Clear? So these 3 types of emissions takes place from the heavy nuclei, and that is the radioactivity. Clear to all of you? Now, law of radioactive decay. Okay. Now suppose at some instant t, number of undecayed nuclei in the given element, that is n. That is n. And in time interval delta t, the number of nuclei decayed, that is delta n. So delta n by delta t, that is the rate of decay. or we can say that is the number of nuclei decayed per unit time. So that delta n by delta t, we can observe this thing experimentally. It depends only on the number of undecayed nuclei. જે undecayed nuclei છે એની ઉપર જ ડિપેન્ડ થાય, ઓબ્વિયસ છે, કારણ કે જે ડીકે થઈને જતા રહ્યા એને તો હવે ક્યાં કઈ લેવા દેવા છે એલિમેન્ટ સાથે, તો ગયા. ઓકે, તો જેટલા ન્યુક્લિયાઈ હજી ડીકે થવાના બાકી છે એની ઉપર આ રેટ ડિપેન્ડ થાય. So delta n by delta t, that is the rate of decay, or we can say the number of nuclei decayed per unit time, that directly proportional to number of undecayed nuclei in the element. Now if we take limit delta t tends to 0, then we can write this delta n by delta t as dn by dt, that proportional to n. So this dn by dt, the rate of decay, that we can write equal to minus lambda into n, where lambda, this constant here, that is called radioactive decay constant. That is called radioactive decay constant. And why here the negative sign is introduced? Because with time, the number of undecayed nuclei n, that continuously decreases. Okay, now see here, from this equation we can write, take this n on left hand side and dt on right hand side. So dn by n equal to minus lambda dt. Now integrating this equation, so integration dn by n equal to minus lambda integration dt. Now suppose at time t equal to 0, the number of undecayed nuclei in the given specimen, that is n0, and we considered at time t the number of undecayed nuclei in the specimen, that is n. So here limits, on right hand side we can take 0 to t, and on left hand side we can take n0 to n. Now integration 1 upon n dn, so that is ln n, here limits n0 to n, and integration dt, that is t, and limit is 0 to t, so simply you can write that is t, so minus lambda into t right hand side. Now here on left hand side, if we substitute the limit, then first n equal to n upper limit, then minus n equal to n0 lower limit. So we can write ln n minus ln n0, that is equal to minus lambda into t. So we can write ln n upon n0 equal to minus lambda into t. So simply we can write therefore n upon n0, that is e raised to minus lambda t. So n equal to n0 e raised to minus lambda t, and this is called law of radioactive decay. And here we can observe this thing, the number of undecayed nuclei that decreases with time exponentially. So if we draw the graph of number of undecayed nuclei versus time t, then the graph will be as shown in this figure. It decreases exponentially. Exponentially means initially rapid decrease will take place, and then after slowly. Clear to all of you? Now suppose here the decay rate that we represent by capital R, then we can say the total decay rate capital R of the sample, that is nothing but the number of nuclei disintegrated per unit time we already discussed, or we can say per second. and the number of nuclei disintegrated or decayed per second, that is called activity. That is called activity. So we can write the activity that is equal to minus dN by dt. Here negative sign represent this thing. As time increases, the activity decreases. Clear? Now we have the equation n equal to n0 e raised to minus lambda t. So if we differentiate this one with respect to time t, then dN by dt, that is n0 e raised to minus lambda t, and of minus lambda t, that is minus lambda. It implies that now we can write R, that is equal to minus n0 e raised to minus lambda t into minus lambda. So R, that is equal to lambda n0 e raised to minus lambda t. Okay. But when here we write n equal to n0 e raised to minus lambda t, then this n0 into e raised to minus lambda t, then we can replace by n. Okay. So R, that is equal to lambda into n. Clear to all of you? Any doubt in
Sir.
this one? Or we can write when R activity, that is lambda into n, where n, that is number of undecayed nuclei at a particular instant, and R, that is the activity at a particular instant. Now, from this particular equation, we can write the initial activity, that is lambda into n0. Clear? Lambda into n, that is the activity at a particular instant, then lambda into n0. N0 is the number of nuclei at time t equal to 0. So this lambda into n0, we can write initial activity. So we can write R equal to R0 e raised to minus lambda t also. Clear to all of you?